flowing into workpiece will tend to generate tensile residual stresses and also reduce cutting forces. Okay, I mean the reduction is not major, it's very minor, but it helps. Okay, so now the question we were to ask is why, right? Why negative rake will generate smaller shear angle. Okay, so the thing is why. So again, I'm going to draw okay, so this one will be negative rake. The other side will be positive rake. Okay, so this one will be negative rake. Maybe I do more towards the okay, so this is negative rake. And then this side is positive rake. Right? So the undeformed chip thickness is the same. Okay. So the undeformed chip, so when the chip goes here, it tends to do this. Right? And then when on the so this is negative rake. And now you can see this is positive rake. Right, these are our two. And this will tend to do this. Okay, so if you look at this angle over here, right, this is known as our shear angle. Okay, then I'm going to label this point A, and I'm going to label this point B. Okay, likewise, I'm going to label this point A. Right. So if you were not to believe me in this, you can do an experiment in your house now. Okay, you take butter. Okay, so if this is your butter, your negative, you take your knife and push it this way. You see how your butter curve? Your butter will have a tight, smaller curving radius, and you have a thicker butter. If you go positive, right? You go positive, cut this way. Make sure it's a knife, not a spoon. Yeah, a spoon is always positive rate angle. Yeah, take a knife, you push through, you'll find finer butter. Okay, you'll find your butter finer, and you'll also realize physically. Try this at home. Okay, with butter. Okay, you will physically see that this is more difficult. This is easier. Okay, that's why ice cream scoop are always positive rate. Right, ice cream scoop is like a spoon, yes or no? When you put in, it's always positive rate. Why? Because it is I mean, in metal cutting sense, our ice cream cutting, okay, it generate less forces, so you can scoop more. Okay, right. Then coming back to here, so now you can see why negative rake, okay, the shear angle is smaller, positive rake is higher.
So, sir, that line where the T is the thickness, that's the chip, that curve, dear?
That
Or
is this is the undeformed chip thickness, the small t, right?
Yeah.
Right. So the big T is here. Okay, the big T. Okay, so this is the big T.
Oh, okay.
This is a big T. Okay. So with that trend, right? So the distance between AB, okay, the distance between AB okay, point AB is known as the length of the shear plane. Okay, it's known as the length of the shear plane. So if I have to draw this in 3D now, right? So this is our point A, and that is our point B. Okay, and then this is our shear angle. So this is 3D now, okay? And then this is our small t. And this term over here from here to here, this is our W. Okay, our W is our width of cut or depth of cut. Okay, so this area over here, I'm shading now. Okay, the area that I'm shading now, this is known as the area of the shear plane. Right? So the area of the shear plane can be calculated by using T omega over sine pi. Okay, where pi is your shear angle. Okay, so cutting forces, if we look at forces, is equal to the shear stress at yield. Okay, why yield? Why the shear stress? Because the shear stress magnitude is lower than the normal stress. Okay, and then you multiply by the area of the shear plane. Okay, you multiply by the area of the shear plane. So if we assume, we're going to assume, we just make an assumption. Okay, over here we just make an assumption. We just assume that tau u is a constant. We just make that assumption. Okay, so what will happen then when we do that? Okay, so I'm going to put in a table now. Okay, I'm going to put in a table. So the table, this is rate angle. Okay, so it's positive and then negative, right? The shear stress over here is constant. Okay, then we look at T omega over sine pi. Okay, so the area, right, for the positive rate angle will be smaller. This one will be larger. So when you get the forces, right, so the forces is area of the shear plane multiplied by the shear stress, right? What we get over here, the forces will be smaller, and this will be what? Larger. Okay. So if I were to draw another trend, Okay, if we were to draw another trend, if we were to draw another trend, so this trend, okay, again, okay, so this trend can be the length or area or the primary shear plane, right? So what is going to happen is that what? Negative rate, your length and area with shear plane is higher than positive. Okay. So on that, we can also look at cutting ratio. Okay, we also can look at cut, and I'll define to you what is cutting ratio. Give me another 5 minutes, then we're done. So cutting ratio R is equal to small t over big T. Okay, so this is your undeformed chip divided by your deformed chip thickness. Okay, and it's always the fact small t will be smaller than big T. Okay, always the fact. Okay, small t will be so, i.e. the R will be always less than what? 1. Okay, so if you look at the context on the shear area, because the shear area affects the length, yes or no, right? So if we look at the deformed chip thickness, okay, if you have, so this is R, right? This is alpha, this is positive, this is negative, this is 0, right? So we know that the deformed chip thickness over here is larger, T is larger, right? Over the other side, big T is smaller, right? Big T is small. So when that's the case, you get this trend on your what? On your cutting ratio, okay? And then finally, the last trend that I want you to see, right? It is going to be your effect of the heat.
What's the R for?
It's just a ratio, just to let you, it's just a ratio that, yeah, just to make things difficult for us, okay? Does that make sense to you? No, right? It's just a term that we tend to use, cutting ratio.
Okay.
Okay. If you ask me when I consult, did I ever use it? The answer is no.
Yeah, I'm trying to figure out what we would use it for.
Hey?
I'm just trying to figure out what I would use that for.
Yeah, so I'll just tell you, no, I'm just following textbook on this one, okay? I mean, if you were to read research papers, okay, they tend to use a lot of cutting ratio. So just to gear you up, lifelong learning. This is more useful than anything else. So this scale over here is proportion of heat okay, heat energy flowing into the workpiece. Okay. So what we get to in here is when you use negative rate, more heat will go into the workpiece. So what does this mean? So if we have a tool over here now, right? This is our pi. Okay. So a lot of heat. Okay. So heat generation Q dot is heat generation rate. If this is equal to 1, Okay. The amount of heat going into the workpiece, so the heat generation is equal to R. Okay. And then the one going over here, the heat generation is equal to 1 minus R. Okay. So you can call this the R value. Okay. So the R value when you going into the workpiece is higher with negative rate when compared to positive. Okay. So with more heat, okay, with more heat energy flowing into the workpiece, material. So you got more heat now, right? Right. The A value, okay, can be reduced during cutting. Okay. So this will generate, or this will lower the stresses, right? This will lower stresses. I'm just going to write here. This will lower the stresses acting on the tool. Okay, acting on the tool. However, the bad news. However, this will also generate tensile residual stresses, especially okay when you have phase transformation from to martensite. Remember we talked about martensite. Okay, is bad news for residual stress. Okay, that's all I have for today. Tomorrow, all the best. Those of you who are having 2PO4 term test, all the best. Okay, don't panic. Dr. Koshi is very reasonable in his question. Okay, on that note,